CRDTs, like sharding, are a powerful tool, and like sharding, we need to understand when it's appropriate to use them. So we have to recognize what the benefits and consequences of using CRDTs are. So in distributed data, CRDTs are stored in memory. That has consequences associated with it. It requires that the entire structure be able to fit into the available memory. So if you have a structure that you are using CRDTs for and it is fairly large and it won't fit into the available memory, then this isn't going to work for you. You have to be able to fit the entire structure in memory. Now, they can be optionally copied to disk. However, the reason that we copy them to disk is to speed up recovery in the case that a replica fails. So if one of the replicas fails, then what we're going to have to do is reestablish that replica, and it's going to need to get its state from somewhere. So it's going to copy that state from one of the other replicas. In order to speed things up, instead what we can do is we can periodically persist the state to disk, so that in the event that a replica fails, we can read that persisted state off of disk and rebuild the CRDTs. But the important distinction here is that during normal operation, all data is still in memory. This isn't the kind of situation where you would store some of the data on disk and some of the data in memory, and when you need something that isn't in memory, you go to disk. That's not what we're doing here. Everything is always stored in memory, and the only reason for putting stuff on disk is so that we have a more rapid recovery. Now, because of these limitations, ACA distributed data and CRDTs are best used for small data sets with infrequent updates that require high availability. So the small data sets should be pretty obvious. And the high availability should be obvious at this point. The infrequent updates are maybe a little less obvious, and so we'll get into why that's important. So why is it important that we do have infrequent updates? So we're going to cover that here, but first let's talk about the data types. So we established already that in order for CRDTs to work, you have to have an appropriate merge function. Not every data type has an appropriate merge function. Sets and maps are pretty easy to do a merge function for. But on the other hand, a list, that's a lot harder, probably impossible. Lists typically have order associated with them. So if you get things out of order, then you end up with a different list. That's not true of a typical unordered set. And remember, one of the criteria of a CRDT is we have to be able to receive things out of order. So lists are hard. The other thing with lists is they can allow duplicates. And again, remember with CRDTs, it's possible we'll get the same state twice, and we need to make sure that we end up with the same result when that happens. With a list, if we get the same state twice, we could end up with 2 entries in a list where we wanted 1, or 1 entry in a list where we wanted 2. And so again, lists don't work very well here. Now we get to the real reason why it's important that we have infrequent updates. So some data types in CRDTs require a complex merge function that leverages tombstones. A tombstone is essentially a marker that shows that something was deleted. So rather than actually removing something from the data structure, we just put a marker on it saying this thing was deleted. That means it's still there. We just marked it as deleted. But what those tombstones mean is they result in data types that get larger and never get smaller. No matter how many times you delete things from that data set, it will never shrink. It always just continues to grow. Because of that, if we have a lot of updates that are constantly adding and removing things, and we are using one of these data structures that leverages tombstones under the hood, then we can end up with something that just continues to grow in memory forever and eventually consumes all available memory and crashes the system. So in some circumstances, depending on the data type, we have to be wary of these tombstones. This is also called CRDT garbage. And there are other data structures that use different types of CRDT garbage. And so it's something that we have to be aware of when we use CRDTs, is that these objects do have additional overhead associated with them, which may cause problems. So how is distributed data, how are CRDTs affected by the CAP theorem? So distributed data is primarily intended to be an availability solution. It is eventually consistent. Depending on the write consistency, so you have a write consistency value that you can use, and depending on what read and write consistency you use, you can push it more towards a consistent approach, a strongly consistent approach. But when you do that, the cost of that is you're sacrificing availability. So for example, you can say, I want my write consistency to be write majority, which basically means I want to write to a majority of my replicas before I consider this operation to be done. Now, when you do that, you're basically allowing, you're saying that if I have, say, 5 nodes in my cluster, I will write to 3 of those nodes. That makes it more consistent, because then when you read back, you can say, well, I want to read from at least 3 of the nodes, and then I can basically determine which one of those is the correct one. And that gives me a strongly consistent approach. However, by doing that, you're saying that if a majority of nodes is not available, then I can't do any writes. So for example, if we said, I want to write to at least 3 nodes, but 3 nodes had failed, leaving us with only 2, well, now I can't do any writes, and I've lost availability at that point. So there is, again, there's a trade-off, just like there is with any of these approaches.